सो वेलकम टू पार्ट 2। ओके, सो इधर हमारे पास है क्रिस्टल लैटिस, स्पेस लैटिस एंड 3D लैटिस. So now basically what's all this that I'm telling you about? So the 3D arrangement of constituent particles in space is called as a 3D lattice or crystal lattice or space lattice. Okay, so what is basically first of all we will be looking at a lattice point. So a lattice point is the position in a crystal lattice where the constituent particle is located. So as we can see this right here in NCRT, this is a lattice point. So this is a crystal lattice, is a two-dimensional one. Be sure there are three-dimensional ones as well. So right here, this point over here, it is a lattice point. Here this one, as you can see. Yep, so that's pretty much it for this. Now next up we have unit cells. So what is a unit cell? Basically a unit cell is the smallest portion of a crystal lattice which generates the entire lattice by repeating itself in different directions. Simple. So it is in short the smallest particle that forms the entire crystal lattice. So well, as we can see here, the unit cell is characterized by edge length A, B, C, and then it has angles alpha, beta and gamma, and the pair of edges are AB, BC and CA. Here we go. It's pretty simple, you can understand this. Okay, so now next up we have unit cell. We have a primitive unit cell and we have a centered unit cell. So what is a primitive unit cell? So you see, for example, as I've drawn this unit cell over here, you have a unit cell and there are unit cells you have this, and the unit cells at the corners, the constituent particles at the corners. So in short, you would have 1 2 3 4 5 6 7 8, but that's not the case here. Just take this as a full sphere, and if you want to keep something at a corner, you will be dividing it in a way like this. But if you want to keep the sphere in this corner, then just take this as a 3D object. So this is sort of a sphere. All right. Okay, so for this sphere to be kept in a corner, you will have to first of all take this part out. But since it is a sphere, when you divide it this way, you will get 8 parts. Okay, so in short, there will be 1/8 of a part here, 1/8 of a part here, 1/8 of a part here. That means that every place there is 1/8 of a part, right? So in short, every piece contributes about 1/8 in a primitive unit cell, and you have a total of 8 pieces. So that ends up being one piece. Okay, one constituent cell. Next we have a centered unit cell. In that, first of all, we have this body centered unit cell, face centered unit cell and end centered unit cell. Okay, body centered unit cell means that it already has primitive. That means we have it at the corner of a cube, but we, as well as that, we have one unit cell that is at the center of the body. So that makes it as a total of 2 unit cells right here. Now next we have face center unit cell. That means corner of cube and the center of the face, right? So over here we have this unit cell, and if we want to keep it on a face, we'll be dividing it by 2, so we get 1/2 of a unit cell. So at every face there are 6 faces, all right, 3 4 5 and 6. So that technically means that we will have 1/2 into 6, so that means 3 plus this 8 over here. So here we will have 4. Hope you understood that, because there are 6 faces, we will be having 6 cells to be kept, and each cell contributes 1/2 because it's halved. All right. And next we have end center, means it is at corner of a cube and it is at any 2 opposite faces. So in short, it is over here and here. Just assume this, and at the corners we already have, so that will make it 1 plus 1, so that makes 2 at end centered. Okay, moving on to the next page. This is just the same thing I said before. A corner contributes to 1/8, and face contributes to 1/2, edge contributes to 1/4, and body center contributes to 1. So what do I mean by edge? You have this cube here, and this edge, if you want to keep a cell, then it would technically be dividing it like this, and the same way from behind, so that makes it to 1/4 part. So that is how an edge contributes to 1/4. Okay, and next up we have body diagonal and face diagonal. Right, a body diagonal contributes to about 4, and a face diagonal contributes to 6. 2 into 6, so that makes it 6. All right, next up we have that there are 8 corners in a cube, and one corner and one is common for 8 cubes. Okay, yeah, we just saw that here. So that is how it makes the contribution. So the contribution is 1/2 of a face. A cube has 6 faces, and each face is common for 2 cubes, so that's why the contribution is 1/2. Okay, a cube has 12 edges, and one edge is common for 4 cubes, so that is how the contribution is 1/4. And in a cube there is one body center and no contribution to the other side, so that makes it 1. So a body center contributes 1. Okay, next up we have the types of unit cells. So in this basically we have primitive or simple unit cells. This means that lattice cube is at the corner of cubes. Lattice point, I mean lattice point. So that means that the effective number, just as I showed before, primitive unit cell means that in this cube we have at every corner, so that makes it up to 1. So the effective number of particles will make it to 1, because we have it every 8 places. Okay, so what's up next? Yep, coordination number. Coordination number is the number of nearest neighbors around a specific particle in a crystal lattice is called coordination number. So the coordination number of primitive cell is 6. How is it? Let me explain it to you. Yep, so let me explain it to you. Here for example you have this point, so from here there will be at least 1 2 3 4 5 and 6, so there will be total of 6 points that will be surrounding this. Okay, done. So the coordination number of a simple cubic cell is 6. So the number of next nearest neighbors, that 8 by 3 2, so that's 12. Okay, so next up we'll be seeing the distance that is between this particle and this particle. Yep, for example this is just a simple cubic cell, so what will be the distance between these two particles that are at opposite sides of a diagonal? So that is root 2a, because here we have this one as a and this one is also a, so that makes it as root 2a between these two particles. Okay, so now next up we have the packing efficiency. What is packing efficiency? It is the volume occupied by atoms upon the volume of a unit cell. Okay, so the formula of packing efficiency is this. In this case here we have the volume right here, the volume of atoms upon the volume of unit cell, and z is the number of effective particles in the unit cell. So if instead of 1 there were 2, in this case there is only 1 here, and this one we are saying the packing efficiency of this one. So in this case what do we get? 4 by 3 pi r cube, that is the area of a sphere. And for example if instead of 1 there were only, so here we have got 8 parts. Yeah, so if instead of that there were only 6, so here instead of z is 1 there would be 3 by 4, because it's 6 by 8 parts. Yeah, I hope you understood that. That's pretty simple. So 4 by 3 pi r cube, that's the area, and I mean that's the volume of the sphere. Sorry, very sorry. And a cube, that's the radius cubed. So here we get pi by 6. So the packing efficiency is 0.5 percentage. And what is the percent void space? That is 100 into the 1 minus packing efficiency, so we get 47.6 percentage, and that is a void space. Now next up is the density of it. So density is mass upon volume. So mass is Z into M upon Na. So N is Avogadro's number 6.023 into 10 raised to the power 23. We all know that E cube is the volume, and Z here is the number of particles in the unit cell. First we saw primitive unit cell. Now next up we will be seeing body centered unit cell. I mean body center cubic unit cell. In this, the lattice points, they are at the corner and at the body center. So that will be 8 into 1 by 8 plus 1 of the body center, that makes it 2. So the first one we had 1, and right now in this we have 2. Okay, that was for primitive, this is for BCC. Okay, remember that. Now next we have the touching coordinates. Okay, so here between 1 and this. Yep, so as I said right over here, the radius between this is root 3a by 2. Okay, so that is 2r. So in short, the radius will be root 3a by 4. Okay, 4, yeah, whatever is written. So root 3a equals to 4r. Okay, so now for the coordination number, the Cn of corner atom in its cell is 1, and the corner atom is shared in 8 cubes. So coordination number is 8, and coordination of body center is 1. Next to the nearest neighbor is 6, and the distance is a. Okay, pretty simple. Now we will be seeing the packing efficiency. What will the packing efficiency be? Z into that volume upon air upon volume. Okay, the total volume of that. So for that we get root 3 by 8 pi, and the void, how much is filled, for that we get 32 percentage, and density is Z into M by Na into a cube. Now next up we are at FCC, face centered cubic. So here the lattice point is at the corner and it is at the face center. So here we get 4. I just told that before. The radius of this we get a by 2 root 2. The radius, I mean the r, the distance, whatever. The coordination number we get is 12. Okay, and what else? Packing efficiency, how much is it? 4 into 4 by 3. So that makes it to pi by 3 root 2. So that will be about 74 percentage, and the yep, that's it. Now moving on to the next one, we have closed pack structure. Now I guess we will be seeing this in part 3. Part 3 will also be releasing soon. Thank you so much for watching. Bye bye.